So, today we will discuss about the determination of coefficient of viscosity of liquid. So, in last class we have demonstrated the experiment in laboratory. So, today we will analyze the data and find out the result. So, basically determination of coefficient of viscosity of liquid. So, we have used Poisson's law for viscous flow of liquid in a capillary tube. The working formula for this experiment was basically eta equal to pi r to the power 4 8 L del P by V by T. So, this is the rate of change of volume, rate of change of volume for a particular pressure difference between the two end of the capillary tube. R is the radius of this capillary tube and L is the length of this capillary tube, right. And this del P pressure difference is measured by manometer. So, basically in two arms what is the difference of height difference of liquid column, generally it is a water. So, this if this height difference is h, so this del P will be h rho g. Okay. So, from this working formula, so we can see that one has to measure r, then length L, and then at different pressure difference what is the change of volume with time. So, volume for a particular time. Okay. So, in experiment in laboratory we have seen that we have measured length using meter scale, or I have not shown, but just I mentioned probably, and radius we have measured using travelling microscope. So, as we have measured in case of surface tension. So, the same way one has to measure, because there also we used capillary tube. So, here the same capillary tube of maybe different radius we have used. So, the same way we have to measure. So, using travelling microscope, or there is another method using mercury, one can also measure the find out the radius of the tube, and then volume V means we will collect water, for a particular time t, the t will measure using the stopwatch, and for a particular time t we will collect water, and then it is a volumetric cylinder. So, directly you can get the measurement reading of this volume of the water, and that for a particular height we have to collect water, and so this will be one set of data, and then you can change the del P, just changing the height, and how to change height, that I mentioned, I have shown you. So, this is the instrument we have used in the laboratory for measuring these the parameters. So, if you measure these parameters, all these parameters, then one can get this eta value. So, this is basically the coefficient of viscosity of water. So, in our case, in our laboratory we have used water. So, Now, so those instrument or tools we have used. So, we have to note it down the list count of those tools. So, meter scale, this list count was 1 millimeter or 0.1 centimeter. So, that is the in error calculation, that is the del L. Then for travelling microscope is the 0.001 centimeter, that is del R. Volumetric cylinder, that scaling, that's yeah. So, the smallest division in that scale was 1 cm cube, 1 milliliter basically, that is centimeter cube. So, that is the basically error, that is del V in measurement of volume V, stopwatch 0.01 second, and manometer. So, this height measurement basically H. So, this is the 1 millimeter, that scale smallest division is 1 millimeter, that is 0.1 centimeter. So, that is the del H, and one has to note it down the temperature of the liquid. So, it is in our laboratory or this temperature of the water, that is 27 degrees centigrade, that is basically room temperature. So, after noting down all this list count of the instrument we have used in the measurement. So, then first we have measured the length of the tube, of the capillary tube. So, basically one tube was used in the measurement. So, always it is difficult to detach it and measure the length or radius of that tube. So, that is why this exactly same tube is kept separately. So, that tube one has we have used for measuring length and radius. So, this table 1 is basically measurement of length of the capillary tube using meter scales. So, as I mentioned for other experiment, that one has to write the list count on top of the table. So, that is 0.1 centimeter. Now, is very simple table. So, we have taken these 3 observations. So, write them and take average mean value of this. Length is basically say 15.2 centimeter. So, just important thing, as I mentioned, that one has to write the unit, whether it is in millimeter or centimeter. So, if one looks at this table, he should understand there should not be missing of this unit, then you see this is meaningless. It will be whether it is millimeter or centimeter or meter. So, if it is missing, if this unit is missing, say then that reading is basically meaningless. So, these are very important part of the recording of data. So, next we have measured radius of the capillary tube. So, that is a table 2, the radius of the capillary tube using travelling microscope. So, for travelling microscope, earlier in case of surface tension, how looks the table that we have seen. So, same table we are using here. So, again this number of observation, then reading of left edge of the whole of the tube, that is say d 1 in centimeter, reading of the right edge of the whole of the tube, that is d 2 centimeter in centimeter, then radius. So, basically difference of these two reading d 1 and d 2, that is the diameter divided by 2, that is the radius in centimeter, and then mean value of r in centimeter, right. So, we have taken 3 observations. So, one has to note down. So, we have discussed in earlier experiments, other experiments. So, same way one has to note it down. So, table should be neat and clean, there should be unit, and number of observation is So, these 3 we have taken. So, finally, we have to note down the mean value. Okay. So, length and radius, the two parameter is measured. Now, important parameters for this experiment, important table for this experiment is basically table 3, this volume of liquid per second for a pressure difference. Okay. So, in this case we will use manometer for measuring the pressure difference. So, this we have to note down the least count of them on the top of the table. So, that is I have done. Okay. So, density of water also in this table we need density of water, rho equal to 1 gram per centimeter cube. Also we need G, that is 980 centimeter per second square. Okay. Now, here I have defined 2 parameters L 1 and L 2. What is L 1 and L 2? The reading of the liquid level of the manometer. Manometer has 2 arm, we have seen. Okay. So, reading of the left arm, that is the if it is L 1, right arm if reading is L 2. So, then L 1 minus L 2 or L 2 minus L 1. So, that will be the height of the liquid column of the water column in the manometer. So, that is the, so that if we define L 1 and L 2, then it is easy to make the table. Otherwise, here you have to write, it will take longer space. Okay. And then it will be difficult to accommodate all these columns in the table. So, that is why to reduce this size of the column, it is we have defined L 1. So, these are tricks you have to use. Okay. So, you see this I am showing the table in different way. So, for a particular experiment you can decide which way you can write. So, even you can make better way than whatever I am showing. So, in different way I am trying to tell you. So, you may also think better way. So, it is not this is table is not unique. Okay. It is not only the table you have to use. So, you can make you can even make it better. So, again this first column number of observation, then L 1, L 2, then H will be L 1 minus L 2 or difference between L 1 and L 2, then corresponding pressure difference H rho g. So, that is why this rho g I need, and that is already this constant is written on top of the table. So, all data is available. So, then for a particular this pressure difference. So, I will collect water, volume of water, okay, in milliliter. So, cm cube, and then how long I will collect this water. So, that is the time of collection in second. Okay. So, then I can calculate this volume per second. Okay. So, rate of change of volume. So, this is the last column of this table. So, now just you set a particular you have to set basically this L1 L2 just for a particular pressure difference. So, you will get L1, say in our laboratory we have taken reading. So, there is a reading was 28.8 and then L2 29.3. So, difference will be 0.5, okay. Corresponding pressure difference if you calculate is the 490. Now, for this 490 pressure difference, now we collect water for 80 second and the volume was 19 milliliter or cm cube. Okay. So, then you can calculate this volume per second. So, this is the 237 into 10 to the power minus 3. Okay. Similarly, for other observation for basically next del P. So, we have taken here 5 reading. So, first and last one I have written here. So, why I have written, so that you will understand, and here also I have written these two all data in this column, because here just to tell you that this so reasonable amount of water you have to collect. For that you have to select time. Okay. So, 80 second for this first observation, for this pressure difference we have collect water for 80 second. Now, generally student will take for 80 second for other cases also. So, they keep this one fixed. Then for this for 80 second next one, next again 80 second for next one. Okay. So, then you see then volume of water will be higher and higher. It is better, but since here this 20 milliliter is a okay, good amount of water. Okay. So, so whether you will take 20 milliliter or 50 milliliter, if you collect more and more, but you have to be optimized. You have to be optimized. Looking at the I think looking at the precision of the measuring tools, one can decide this value. So, here this volumetric cylinder, this error is actually this least count is 1 cm cube. So, if you collect 20, so 1 by 20, okay, 1 by 20 means it will be I think 0.05. So, error will be 5%, error will be 5%. So, to reduce error, even I think it is better to collect water slightly more. So, it can be I think around 40 milliliter to 50 milliliter, that would be better. Anyway, so here we have collected for 80 seconds. So, it is better to collect for I think 2-3 minutes initially for this one. Okay. Then next one your time will be reduced, because pressure is becoming higher. So, the speed of the water will be higher. Okay. So, you will get higher amount of water for this same time. So, to keep this amount of water in the same range, so you can reduce the time. Okay. So, here whatever this actually my our lab technician they have taken data. So, just I have I am showing those data, but I would suggest you that 5% error is you can see this from this measurement 5% on this volume measurement error will be 5%. So, I think you should reduce it. So, at least come down to at least half of it 2.5% or 2%. Okay. So, we should collect water more time for more time, okay. Because I cannot increase this pressure too much, because then this flow of water it will not be then this it should be streamline motion, okay. Otherwise it will be turbulent. So, then this formula will not working formula will not be valid. So, I cannot use this very high pressure difference, okay. So, there is a limit. So, anyway, so if pressure difference is lower, so you have to spend more time to collect water. So, so here I would prefer to collect at least 40 to 50 milliliter for each cases, around 40 to 50 milliliter. So, then basically here this volume per second is a 237 into 10 to the minus 3, and this last one this pressure difference is 1666, and corresponding volume of water per second. So, that is 725. So, now you have data 5 data, you have 5 data for 5 difference of what difference of 5 difference of pressure, and then this the 5 volume per second, this rate of water volume the rate of change of water, okay, in volume basically. So, that is the 5 data we have. So, why I have taken 5, why not 3? Because this from working formula, as I told earlier also, that this eta equal to this one, okay. So, basically as I told, this table 3 is important one. So, here for different pressure difference, if we measure this different V by T, so then we will plot graph of this del P versus, actually this should be x, because we are changing and we are collecting this one. So, this should be y, okay. So, rate of change of volume versus this pressure difference. If you plot this graph, then from that graph we will get slope, okay. So, that slope is basically, then we can use the slope in this calculation. So, that slope will be, we will replace this by the slope, okay. So, this value we will get, that is the basically slope of the graph, or inverse of the slope of the graph, okay. So, that slope we will use here, and R and L are already we have this data, average R, average L. So, we can calculate eta. So, that is the purpose we have taken 5 data, okay. Now, we have to plot graph, okay. So, yeah, so just graph plot volume rate versus pressure difference. So, this x axis I have taken pressure difference, and y axis we have taken V by T, okay. So, look at the data, So, x axis is the pressure difference is the 490 to 1666. So, this is the lowest value and this is the highest value, okay. So, depending on that one should choose the scale of this axis. So, that is why here you see instead of 0 I have taken 400, okay, and this upper one I have taken 2000. So, in between I have to scale 400, 500. What is the each box will be, what is the value. So, that one has to define here one smallest box, okay, is what is the value. So, that you should mention for x axis and for y axis, okay. And of course, you have to write this level, you have to label this one like this with unit. Similarly, y axis, okay. Y axis, what was this? It was 237 to 725. So, I have taken from 200 scale, I have taken 200 to 725. Of course, it will be, it has to be, I think 10 to the power minus 3, 10 to the power minus 3. Okay. So, now this all data have this 10 to the minus 3. So, y axis you see v by t in cm cube per second. Okay. So, here, so this factor we can write into 10 to the power minus 3. So, here this I should write. So, just later on I have written this one. So, actually should write this one here. So, actually this unit is 10 to the power minus 3 cm cube per second. Okay. So, whatever this in bracket we are writing, whatever that is 200, whatever the unit, it is cm cube per second, that is what the meaning, right. So, now if I write this way, so then 200 into 10 to the power minus 3 cm cube per second. So, instead of here you can write here this one 10 to the minus 3 means 0.2 and here 0.8. Okay. But so here 0.1 you can, but if it is 10 to the power say minus 17 or minus 21. Okay. So, that you cannot, here either you can write here itself you can define 10 to the power minus 3 for here 0.2 into 10 to the power minus 3, 0.8 into 10 to the power minus 3. Okay. Sorry, 0.2 this fine or 0.8, or you can write 200 into 10 to the minus 3, 800 into 10 to the minus 3. Okay. So, but then you need longer space. So, or always you are repeating the same thing. So, to avoid that one, and it is a convenient way to represent. Okay. So, people prefer to write this way. So, this is the another way, just I am showing another way to write or labeling this axis. Okay, this is valid for x axis also, y axis also. So, depending on your data, you have to decide how to write. Okay. So, this just that is why I have just noted down this reading, okay, to tell you about this the way of writing. So, just then you have five data points. So, you have to plot these 5 data points, and then you have to it is basically it will be from equation one can see this, it will be straight line. So, you should draw a straight line, average straight line, okay, and from there you find out the slope, slope you know. So, these 2 points you have taken. Now, this difference of this y axis, these 2 value is v by t, and this defines in x axis these 2 points. So, you can find out and then that will be del phi. So, this slope. So, one has to find out the slope and then from the slope. So, now already you have the slope. Now, this slope we will use for calculation. So, then we are basically next step is to is calculation. So, slope this you note down. So, I have not plotted the points, but I know this from the data we have plotted and this we calculated the slope is say this. So, we have to write this value from where I got this from graph. Okay. Now, eta value was this. So, this I can now write. So, our slope is v by t by del phi. Okay. So, here del p by v by t. So, it is a basically inverse of slope. So, I have written slope 1 by slope. Okay. So, slope from graph I got r and l from table 2 just noted down here and from table 1. Okay. So, now I can calculate the eta value. Okay. Now, this is the universal constant, this viscosity of water at a particular temperature. So, that is available from data. Okay. So, that value true value of this eta for water at 27 you should write and then compare how good your result. Okay. So, next is error analysis. So, it is very simple and you know already I have discussed many times for other experiments. So, here just simply this the formula for the error and from there you find out the eta, because del eta is already you have here. So, other also or data you have. So, you find out del eta. So, now write result eta equal to this whatever value you got here plus minus del eta. Okay. So, this is the systematic way you have to proceed, and so this is for true for all experiment. So, just last 3-4 experiment I discussed and everywhere I am telling the same things. Later on after that whatever experiment we will do I will not tell much about this, because already you know, otherwise it will be just boring. Okay. So, initially for few experiment I told in details, but next for other experiment I will just mention. Okay. So, same way you should proceed. So, then I have not told earlier for other experiment, next important step it should be discussion. Okay. So, discussion there point 1, 2, 3, one point could be this whatever the true value, okay, standard value of the viscosity, okay, but your value is deviated. It is if it is very close to that, then you should in discussion you need a place where you should tell your words, right. So, you can write that your whatever you experimentally you got this eta value that is very close to the true value. So, your experiment your measurement is very good, or there may be deviation from the true value. So, then you have to tell that one, and you can discuss why this from where this deviation is coming. Okay. So, these things this is the place where you have to mention, and then some precautions. Okay. Like here r to the power 4. Okay. In radius, in formula radius r to the power 4. So, in error you have seen this, for if error in the measurement r, this is del r, it is not del r by r, it is a 4 del r by r. So, whatever the del r in your this least count of your instrument. So, you have to take better instrument, means this its least count should be very small, otherwise error will be higher. So, here you should use better list count. Okay. So, that is what you can discuss in the. So, you have taken precaution for measuring the radius of the tube. So, your list count is 0.001 centimeter. So, this very small list count. So, because this here error depends on the is the error will be 4 times basically of the list count. Okay. Not error means whatever yeah. So, error in the measurement. So, there is the 4 times of the list count. So, one has to. So, this type of precaution you have to tell, you have to write. Okay. So, that is the next that is that item generally we keep, it is the precautions. Okay. What precaution one should take during this experiment. So, that is what you should write. Okay. So, yes, so I think I have analyzed in details. Okay. And for other experiment, I think this I will tell about more about discussion and precautions more. Okay. Because I have not mentioned for other experiment, previous experiment, experimental discussion. So, but about table etc., I told I discuss in detail. So, that I will reduce time there, but I will spend more time on discussion precautions for other experiment. So, I will stop here. Thank you for your attention.